Hi, I'm Chris Brown, and this is the 12th lecture in the second part of axiomatic design to manufacturing processes. This lecture is about manufacturing process analysis in the context of axiomatic design. So first, let's consider facts versus principles. Facts. This is knowledge relating FRs and DPs, or DPs and PVs. So this is where researchers have set up experiments to discover what the relationships might be in these situations. Now, the most lectures, many of the lectures, and technical papers are about facts. And my apologies. And these facts are limited to the in applicability to the situation of the experiment. Principles, on the other hand, have got broad applicability and things like design theory. So they tell us that there are FRs, DPs, and PVs, and that there's axiom structures and process. Now, manufacturing theory, of course, that we've developed earlier, says FR0 is add value, and the selection criteria or a constraint could be minimize cost. Now, when you're doing literature searches on manufacturing processes to support your project work or the different homeworks, mostly what you're looking at is facts. And what you're trying to do is sort out FRs, DPs, and PVs where the authors have probably not used these terms because most of the authors aren't familiar with axiomatic design, but they're still writing about manufacturing processes. Now, the first thing you want to do in your literature search is be quite process specific so that you're looking at the process that you're interested in and the situation that you're interested in to see what the closest thing is to that. Now, generally you don't find something exactly what you're doing, although if you have, you can be doing some reproducibility work to see if you can reproduce what the other people have done. But generally what you have to do is look and see, all right, well, who's used a similar method, who's used a similar analysis, who's used similar materials, who's looked at similar processes, and try to sort out in a kind of multi-dimensional space where the works are that are closest to what you're doing in each of these dimensions, like methods, analysis, materials. So first you start off being process specific. Now you may not find anything, and then you might expand to the basic sciences or more basic engineering that might be related to these processes. So if you're looking at a drawing process, for example, you might look at some basic physics on mass transfer. All right, so we discussed previously processes versus systems. Let's keep this in mind because we want to be working on processes. So we're looking at things like where the tool meets the workpiece, chip formation and machining, maybe the machine tools as well. And so we'd like to leave out the systems. All right, a process. Now this is where we apply energy to do work, to make changes that add value. So this can be the geometry if we're looking at mechanical parts. So we might do this by adding material, removing material, or deforming material to change the geometry. Could be assembly. So we've got some different components that need to be assembled somehow. Might be modifying the microstructure using some material science to get the right kind of strength or fatigue. Might be modifying the composition. This happens a lot in microelectronics where you have to diffuse in elements in order to get the integrated circuits to work. But also it could be in making gears where you want to case harden them or other kinds of composition changes. Of course, if you're looking at basic metallurgy, there might be a lot of that, or materials. So also you might add or remove residual stresses from the materials in order to create a surface that might be more resistant to fatigue, for example. So there's lots of different processes, and I've got a few pictures here so we can think about these. This is open die forging. This is quite a large part, and you can see here's the die and the hammer that comes down, and there is the sort of hammer master there. and turning this with a large chain and tongs. And obviously it's quite hot. Speaking of forging, one of my favorites then is, of course, here in Worcester, Wyman Gordon, with a very large 50,000-ton press, 5 stories high. And just to get an idea of how big this is, there's a person standing next to it. Rolling. Also, this is Simmons now has bought Morgan Construction, and they make rolling mills here in Worcester. And so here is some rod or rod-like material coming off a rolling mill. And you can see that it's quite hot by the color, and that it's going into loops because it comes off so fast that it would, if you didn't loop it, it would be hard to control. So the other thing here is you can see some heat treatment, and controlling the heat loss, you have these doors that you can put down to change how fast this is cooling off. Machining, and we're going to look at more in more detail machining, and right here where the tool meets the workpiece, we can see the chips coming off and falling down, and so that's machining by turning. And then in milling, we can see here the chips forming, material removal again. And here's the little bit of hard metal with a titanium nitride coating that's doing the work and scraping off the little chips. And we'll look at that in more detail later. So what we'd like to do for analysis is try to find commonalities. And so, so here we might look at fundamental physics and see how this applies. Now, when we're doing the deformations or removing chips, actually, which is a special deformation case, as we'll see later, force balance is very useful. So Newton's laws need to apply, and we can make use of those. Laws of conservation. Now, conservation of mass, as long as we're not into nuclear reactions, is the basic physics principle. But the density often changes, are not important when we're looking at manufacturing analyses. And so, so sometimes we simplify this and say, well, let's assume the density is constant enough, and we'll do conservation of volume. Also, conservation of energy into work and heat is one of the basic analyses we can use. And then there's a lot in material science. So you notice we were deforming materials, adding materials. So deformation and strength are issues here. So the mechanics of materials, plasticity, heat treatment, microstructure are all things that could go into manufacturing analyses. So what sorts of themes should we be using as we try to decompose this problem of analyzing manufacturing processes and understand what's going on? Well, so if we're supplying energy to do work, and this is what has to be done in order to add value, then energy work seems like a good theme. So we're doing work on materials to produce shapes and properties that a customer would value. So one of the things we can do when we're analyzing manufacturing processes is to follow the energy. So the energy initially is coming usually from outside someplace, and where is the work being done, and where is the value being added? Now, since we're looking at energy, let's just take a moment to think about it and how this concept of energy has developed, just like we took a look to see how thought, what people thought of thought. Well, energy comes from a Greek word that means, roughly translated, living force, energia. And many people had discussed that. Newton thought it was momentum, MV, and many people did, I guess, in Newton's time, believed that mass times velocity was the sort of the living force. Now, Émilie de Châtelet, a woman who translated Newton's Principia into French, and was aware of some experiments that were done in the Netherlands, dropping metal spheres into mud and measuring how far they penetrated, figured out that energy, and was able to show that energy from mechanics is 1/2 mv squared. So this is quite a useful discovery back in the 1700s when Émilie did this work. Count Rumford is another interesting character. He's actually born in Massachusetts, ends up on the wrong side of the American Revolution from an American perspective, leaves North America and works in Europe, ends up in Germany making cannons. And one of the interesting things he found out is that in boring out the cannons, you can boil water. So boring is a machining operation in order to size the inside of the cannon. This comes up again in a moment. But the idea that there is work going on in order to remove the material, and it's that work that's heating up the environment and not something being released from the material itself, is kind of the new idea. So Rumford actually got a couple of horses to walk around in circles and power the boring out of the cannon, submerge the whole thing in a barrel of water. And the stories are that after about 2 hours of this, he got the water to boil. Now, he didn't follow up with sort of the work energy equivalent. That had to wait another few years for Joule's famous experiment. All right, the Industrial Revolution, manufacturing. So this is kind of an interesting coupling here. The steam engine is key to the Industrial Revolution. So it frees factories from water power and can be used for transportation. So it enables more different placing of the manufacturing and transporting of manufactured goods, which you need to do because the manufacturing is centered in factories at that time. Now, the interesting thing is, while this is important for enabling the Industrial Revolution, it itself, the steam engine, was enabled by a manufacturing process. Let's take a look. So Wilkinson's boring mill is sometimes credited with enabling the Watts's steam engine. And the reason was, and you can see here in its cutaway, this is the cylinder. Now, previous experience had been boring out cannons, which didn't have the same tolerances. The tricky thing was to get a piston to slide inside a cylinder, but fitting tightly enough in the cylinder so that the steam can build up pressure to do work, but not so tight as that it seizes on the cylinder. Or there's problems sliding in the cylinder. So there's a very small tolerance band. And in order to hold that, you needed a different kind of process than boring out the cannon. And so here we can see tie downs to stabilize the workpiece, which is here. And then the tooling is pulled through it, and the power is being supplied here, mechanical work through the turning of the gears. So Wilkinson's boring machine, 1775, a key to the Industrial Revolution. Here's somebody else's boring mill, and a somewhat similar thing where you've got some gears and the energy's coming from water or someplace, and then in this case you're sliding the cylinder over the cutting tool, which is here. And that's boring out this cylinder, so you get the tolerance is good enough for the function, create the value. The value is only there if you could get the tolerances well enough, if you could produce them well enough. All right, so enabling modern manufacturing is energy, tools, and control. So first, we need to deliver energy to do work, and therefore we need to get some force and movement. And then the issue is reproducibility, controlling the position, so we can make parts that are similar enough so that we can do mass production and most of the time want interchangeability. Now, controlling the position and computer controls come in, and different kinds of numerical controls come in starting in the 1950s. And some of this means that we can have mass customization by controlling the position, not always to do the same thing, but to do different kinds of things well. Now, so more recently, we're seeing additive manufacturing, and again, this is some application of energy. In this case, we're looking at laser sintering, and we're looking at some sort of metal powder here, which is being heated up by the laser and fusing. So it's adding to the structure every time it comes around. Now, one of the issues that we'll discuss in more detail later is that this is warming up the material here, heating it up enough to melt. So the adjacent material is seeing some heat process or some thermal processing, which is sort of a consequence of getting the material near it to sinter and not always perhaps desirable. Anyway, again, the notes on the literature search: first process specific, then expand to the basic sciences related to the process. All right, thank you for your attention.